So today is going to be more of the same. Derivatives of a function, day 3. We want to sketch the graph of a continuous function. So that's important that we read that continuous function. So there's no breaks in the graph, okay? No holes, no jump discontinuities, no removable discontinuities. In other words, no holes, and no infinite discontinuities, okay? All right, so from this, we know that f of -1 is equal to 2. So at -1, we know our value of the function is 2. So that would be this point right here that we plot. And so my function is going to have to go through that point. And then I know the derivative is -2 when x is less than 2, but I know it's 3 when x is greater than 2. So I'm going to make a mark on my graph right here at 2. And I know what I know from this is that to the left of 2, my slope is always -2. So we have to go down 2 and right 1 when x is less than 2. So this point right here is to the left of 2. So it takes on this condition right here. So we have, from this point, we need to go down 2 and right 1, and that'd be a point right there. And then down 2 and right 1, and that'd be a point right there. And then down 2 and right 1. And now we're at 2 and we're going to stop. Now we could add some more points up here because we could go up 2 and left 1. The up 2 would be positive and the left would make it be negative. So up 2 and left 1, up 2 and left 1, and then up 2 and left 1. Okay, so I'm going to connect those, and you wouldn't have to do that many points. Okay, so we know our function is going through that point, and this is true. And I know it's, I should have said this, I know it's a line because only lines have derivatives that are a constant slope, right? Because anywhere on this line, if you try to take the derivative here, it's -2. If you try to take the derivative here, it's -2. If you try to take the derivative here, it's -2. Because the slope isn't changing, it's always constant, okay? So to the right of this, right to the right of x equals 2, we know our slope is always going to be 3. So from this point right here at 2, we're going to go up 3, 1, 2, 3, and to the right 1. So 1, 2, 3, and right 1, and we can get a bunch of points here. 1, 2, 3, right 1, 1, 2, 3, right 1, and then we don't have 3 to go up anymore. So then I'm going to connect those, this point, with all of these. Okay, and that's the shape it takes on. Okay, now the next two, and I should say this, there's a reason there's no derivative right here, okay? There's no derivative at x equals 2 because on the left side, the derivative would be -2. If we did a left-hand derivative, it would be -2, and the right-hand derivative would be 3, and the problem is those aren't the same, and that's why we don't have a derivative at x equals 2. Okay, so now we're going to do some problems like we did yesterday with one-sided and piecewise functions. Okay. Okay, so using one-sided derivatives, show that the function f of x is equal to -x plus 5 when x is less than or equal to 1, and x squared minus 4x plus 5 when x is greater than 1 does not have a derivative at x equals 1. So right here is x equals 1, okay, and it doesn't have a derivative here, okay? Now, I want to talk about this is the anchor point, all right? This is the point that's on the function, okay? And if I do a left-hand derivative at this point, it's going to be on this line, okay? And so right at this point, the left-hand derivative is going to be the slope of this line, which we should be able to tell it's -1, okay? Now, as we bring a point in, this is the anchor point. This is where we're trying to find the derivative at because that's the value of the function when x equals 1, okay? And I know that because it's a closed dot. As I come in here and bring this second point and do the right-hand derivative, I want you to visualize this because I kind of already know what I'm going to get out of this. And I would like for you to be able to do the same thing. If I connect these, I have a vertical line, right? I have a straight vertical line, which means the slope is either going to be infinity or -infinity, all right? Now, just before I'm connecting this closed dot with this open dot, right before it, I'm going this way, right? And this is going down from left to right, which would mean it has a negative slope. So just all the slopes until we get right in the vertical are all negative, which means the slope when we go absolute vertical is going to be negative infinity. And I'm going to show you that that's going to be true, okay? All right, so let's do the right-hand derivative. Actually, let's do the left-hand derivative. So left-hand derivative, okay, and we got to pay attention to the notation. There's no notation for the left-hand derivative, okay? We just have to write the words out. Left-hand derivative at x equals 1. So the left-hand derivative, we're gonna write the limit as h approaches 0 from the left of f of 1 plus h minus f of 1 all over 1 plus h minus 1, which would just be h. Okay, so if we're going to approach this from the left, right, this h is going to be negative, right, because we're approaching h from 0 from the left. So that means this is going to be small. 1 plus h is going to be smaller than 1. And let me get a pin, a different colored pin. Hold on a second. All right, so like I was saying, okay, this 1 plus h, because h is negative, this value is going to be smaller than 1. And when it's smaller than 1, we use the line negative x plus 5. Okay, so this is going to equal the limit as h approaches 0 from the left of, and I'm going to put a bracket in here, and it's going to be negative of 1 plus h plus the 5. And then minus f of 1. Okay, so when it's 1, we use the line again, right? So that would be negative 1 plus the 5 all over h. Okay, so this is equal to the limit as h approaches 0 from the left, and this would be negative 1 minus h plus 5, and then this would be plus 1 minus 5 all over h, and then this is equal to the limit as h approaches 0 from the left. My 1's cancel out, my 5's cancel out. I'm left with negative h over h, which is equal to the limit as h approaches 0 from the left of negative 1, because the h's cancel. And so because I'm taking the limit of a constant, that's always going to be the constant. So my answer is negative 1. So if I pick this point and pick another point on here, anytime I do that, I'm going to get a slope of negative 1. All right, let's do the right-hand derivative. And that's right, that makes sense because this slope has, this is the anchor point, and we're going to the left of it to get and bringing it in. So that point, the slope between those 2 points is always going to be negative 1, even if you bring it in, okay? That's why it's constant. So the limit as h approaches, I didn't mean to write that. Here, looking for my whiteout. I meant to write right-hand derivative. Okay, so this one's going to be, I'm going to leave a little bit of space so I can write, the limit as h approaches 0 from the right of, again, f of 1 plus h minus f of 1 all over h. And remember I said just a minute ago, okay, I think this is going to come out to be negative infinity, all right? So this is equal to, and now we got to figure out, okay, this, we know what to put, if it's 1, we know which piece to put it into, but how about 1 plus h? Okay, well, it depends on what h is, right? And in this case, h is positive. So when we take 1 and add a positive h value here, right here, this is going to be bigger than 1. Okay, if that's bigger than 1, then that means we're going to have to put it into the quadratic. Okay, so this is the limit as h approaches 0 from the right of, I'm going to use a bracket here. This is going to be 1 plus h squared minus 4 times 1 plus h, and then plus the 5. and then close the bracket, and then minus. And then right here, this is going to be, we're going to put 1 in to the line. So it's going to be negative 1 plus 5 all over h. This is going to equal the limit as h approaches 0 from the right. I'm double checking to make sure you guys can see it on the screen. All right. I don't want to make the same mistakes I made yesterday and have to record this 3 or 4 times. So this would be 1 plus 2h plus h squared minus 4 minus 4h plus 5, and then plus 1 minus 5. All over h. And we can clean this up a little bit. This would be the limit as h approaches 0 from the right. Okay, so I have 1 and a negative 4, which makes negative 3. And this 5 cancels with this 5, right? So I have 1 and 1, which makes 2. So that's negative 2. And then I have 2h and a negative 4h. So that makes negative 2h. And then I have plus h squared all over h. Now let me just double check. Okay, so we got 1 and negative 4, which makes negative 3. Negative 3 plus 1 is negative 2. Yeah, and these two 5s cancel. All right, and then we had 2h and negative 4h, negative 2h. Because it's easy to make a mistake here. And then plus h squared. Okay, so now I have some room to go to the right. Okay, so equals the limit. And I did it. Dang it. I said I wasn't going to do it, and I did it, huh? Okay, but I don't think it was that bad. All right. So this is the limit as h approaches 0 from the right of, okay, I'm going to break this up. I'm going to write this as negative 2 over h. And this is going to be minus 2. And this becomes plus h. So I wrote that as single fractions, and I just did a common denominator of h, right? And I reduced it all at once, okay? Okay, so h is going to go to 0. So that means this is going to be 0. So we can ignore this because that's going to be 0. We have the minus 2. Okay, so right here, we're putting h is approaching 0. So this is getting closer and closer to 0, but it's going to be positive, right? So if this is going to be 0, that's going to cause this to either be infinity or negative infinity. This is positive, but this is negative, so that's going to make this become negative infinity. So negative infinity minus 2. Well, negative infinity minus 2, the minus 2 is insignificant compared to negative infinity. So this becomes just simply negative infinity, like I said. Because right when I connect this point, that's where I'm trying to find the derivative at, right? When I connect this point with this point on this curve, that'd be a vertical line. And just before it, it was a negative, the line had a negative slope, right? Right in here, okay? So what does that mean? The limit as h approaches 0 from the left of f of, and let me slide it up, I caught myself, 1 plus h minus f of 1 over h does not equal the limit as h approaches 0 from the right of f of 1 plus h minus f of 1 over h. So we would say the limit as h approaches 0 of f of 1 plus h minus f of 1 over h does not exist, which also means, and these are interchangeable actually, f prime of 1 does not exist. So f prime at the limit as h approaches 0, that is the derivative at 1, right, for our function. So f prime of 1 does not exist because this is equivalent to f prime of 1. All right, I'm going to do better on sliding this up for the next problem, okay? So we have one more problem to do. All right, so on this problem, we're using a one-sided derivative to show that the function f of x, which is made up of two pieces. It's x plus 3 when x is less than or equal to 2, and x squared minus 6x plus 13 when x is greater than 2. And we want to show that it does not have a derivative at x equals 2 where it switches, okay? And that's this point right here. Now, the left-hand derivative would wind up being the slope of this line because that's a straight line. So any derivative at that point, and that anchor point's on this line, okay, then it would have a slope of, and it looks like it's 1, okay? So we should get a left-hand derivative that's 1. So we can kind of estimate this even before we even start doing the calculus on it, all right? Now this one right here, we're going to be coming up. So this is the anchor point. So that's the fixed point, and we're bringing another point in. And you got to imagine like drawing these lines, right? Connecting them, right? And that point gets closer and closer and closer and closer and closer. Now it doesn't go vertical this time. It goes right about this direction right here, right? So it looks like it might be like a slope of -2. If you tried to extend this out a little bit with a straight line, it looks like it might be like maybe -2. So down 2 and right 1, maybe. We'll find out. Let's see. Okay. So here we go. All right. So we're going to first do a right hand derivative at x equals 2. Okay, so we got to do the right hand derivative and the left hand derivative. Okay, there is no notation except for the limit statement to write a right hand derivative. So please do not, this is wrong. In fact, I will mark it completely wrong because you're communicating something and you don't mean it. Okay, and that is don't write f prime of 2. Okay, that's when we know the derivative exists and we're going to go from both sides. Okay, all right, so what we're going to write is the limit as h. You know, I said right hand and I meant left hand. I want to do the left hand first. Sorry. Left hand, which means this is going to change, okay? So the limit as h approaches 0 from the left, okay, of f of 2 plus h minus f of 2 all over h. Okay, so this 2 plus h. Now, is this 2 plus h? Is this 2 plus h bigger than 2 or less than 2? Because that determines which piece we're going to grab, okay? So h is approaching 0 from the left. So that means these h values, as they get closer and closer to 0, they're all negative. All of them are negative, which makes this smaller than 2. Okay, so then that makes this the limit. And now we know what piece to put it into, okay? That's why I talk about that. Okay, so it's smaller than 2 or less than 2. That would be this one, right? So we're going to put it into the function x plus 3, okay? So this is going to be, I'm going to use a bracket here, 2 plus h. That's showing I'm putting in for x, and then plus 3. Close the bracket, and then minus bracket, and now we're going to put 2 in. Well, which function do we use when we put 2 in? Well, this is saying we use this one when x is less than 2, but also when it's equal to 2. So we're going to use the x plus 3 again, right? So we're going to put in 2. That's putting it in for x, and then plus 3. All over h. Okay, so then this becomes the limit as h approaches 0 from the left, and this becomes 2 plus h plus 3, or h plus 5, or 5 plus h, either way. And this is minus 5 over h. Well, these 5s, you know, we're adding 5 and taking away 5, so this becomes the limit as h approaches 0 from the left of h over h, which then becomes, I'm gonna go sideways as long as I can. The limit as h approaches 0 from the left of 1, and the limit of a constant is always that constant, so this is 1. And so, yeah, that's what we said, right? The slope should be 1 on this side, on the left-hand side of that point, okay? All right, so the next one, let's go right-hand derivative. At x equals 2. x equals 2. Again, please listen to this because I have this happen all the time on the test, and a lot of students do it, and you get a 0 on this problem because you're telling me you really don't understand and you don't know the language of this. Do not, on these left hand and right hand, write f prime of 2. Don't write it, okay? Because that means the derivative exists at 2, and we're actually showing that it doesn't, okay? So don't do that, okay? All right, so here we go. Enough of me, all right? Limit as h approaches 0 from the right. That will cause a right-hand derivative, f of 2 plus h minus f of 2 all over h. Okay, now, this 2, we know what to do with, right? We know what piece to put it into from this part up here. Okay, the 2 plus h, which piece do I put it into? Well, h is approaching 0 from the right. That means your numbers you're putting in for h are actually a little bit bigger than 0, which means they're positive, which makes this bigger than 2. Okay, if that's bigger than 2 or larger than 2 or greater than 2, then we have to put it into the x squared minus 6x plus 13 piece of the function, okay? And that's what we have to do. So this becomes the limit as h approaches 0 from the right of, and bracket, 2 plus h squared minus 6 times 2 plus h plus 13, close the bracket, minus bracket. And then, okay, we're going to put 2 in, right? And we use the line again. So that'd be 2 plus 3. You guys, you wouldn't have to have parentheses around the 2. It would not be wrong if you didn't. Sometimes I would write it and sometimes I wouldn't. Okay, now please, 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 I'm going to say this over and over again. This, you can't square the 2 and square the h and you're done. No, it's more than that, right? It's 2 plus h by 2 plus h. It's a square and you're missing part of it, okay, if you do that. So then this is equivalent to the limit as h approaches 0 from the right. And maybe you've done this so much now that you're starting to pick up on the pattern. It's going to be 2 squared, which is 4, plus we're going to multiply and double this. So that'd be 2h doubled would be 4h. And then plus h squared. And then minus 12. And then minus 6h. And then plus 13. And then minus the 5 right here. All over h. Okay, I honestly think it's going to be easier if we clean this up before we mess with the minus 5, okay? So this is equal to the limit as h approaches 0 from the right of, okay, so this would be 4 minus 12, which would be negative 8, and then negative 8 plus the 13 would give you 5, okay? So we have 5, and then we have this 4h, and then minus 2h, that's minus 6h, which gives you minus 2h, and then plus the h squared, and then minus the 5, all over h. Okay, so these 5s cancel. So this becomes the limit as h approaches 0 from the right of negative 2h plus h squared all over h. So we could factor an h out, or you could divide each of these by h. And that would leave you with the limit as h approaches 0 from the right of negative 2h over h. I'm going to put a parenthesis now. Negative 2h over h plus h squared over h. And then that's equivalent to the limit as h approaches 0 from the right of, and then this becomes negative 2 plus h. And now we can do a direct substitution, and this is going to become negative 2. So our slope is, so our right-hand derivative is negative 2 at x equals 2, but our left-hand derivative is 1. They're not equal to each other, okay? For a derivative to exist, the limit has to exist, which means the one-sided limits have to exist, and they don't, right? So what we could say is the limit as h approaches 0 from the left, and I just realized you cannot see it. I was going to be good and I wasn't. all right? The limit as h approaches 0 from the left of f of 2 plus h minus f of 2 over h does not equal the limit as h approaches 0 from the right of f of 2 plus h minus f of 2 over h. Okay, and because that they're not equal to each other, that means the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, this limit does not exist, which also means f prime of 2 does not exist, because these are the same, all right? Okay, so what we showed is the function f does not have a derivative at x equals 2, because otherwise we get a number for that, all right? Okay, guys, that's it for today.